Welcome to a refresher lesson for finding zeros of polynomial functions. As this is a bit of a complex topic, I have broken it into two parts. This video will focus on finding real zeros and corresponds to the examples on a worksheet packet that can be found at my Teachers Pay Teacher store. The other part will review finding all zeros and also can be found at Teachers Pay Teachers and on my YouTube page. In this video, I will explain the skills and steps necessary to complete all of the examples on the Finding Real Zeros worksheet. Please feel free to skip around to engage in the concepts with which you would like some help. So, our first few examples are not really going to get into finding the zeros yet. It's going to set us up for being able to do that. So in order to be able to find real zeros, or really any zeros for a polynomial function, we first need to be comfortable with doing synthetic division. So synthetic division is kind of a shortcut way of doing division, but it only works in certain cases. The big thing that needs to be true is that we need to be dividing by something that is in an x minus k form. Now, it could be x plus something, meaning k is a negative number, but it needs to be a linear binomial and usually without a leading coefficient. Okay, so we want this x minus k form. That should be our divisor, what we are dividing by. Okay, and then the other thing that we just want to be sure when we're working with this is that the dividend, which is what we call this part of the problem, that it is written with our terms in descending order of the exponents, which this one is. We start with a 4 and then go down to a 2, a 1, and then our constant. So to set up synthetic division, we start by taking the coefficients on each of our terms. So technically the coefficient here for x to the fourth is going to be a 1. And then we have the coefficient of negative 5 here on x squared. We have the positive 3 here on x, and then the negative 8 here, which is our constant. Now notice we do not have an x cubed term. So we assume that the coefficient on x cubed must have been a 0, and we're going to include that in this first line that we write down of just the coefficients. So if I'm starting with my x to the fourth term, it had a coefficient of 1. X cubed, we would say, had a coefficient of 0. X squared has a coefficient of negative 5. X has a coefficient of 3, and then our constant of negative 8. Okay, and then from our divisor, we are going to take the k value and put it out here in a little half box. Now again, notice the form of the divisor should be x minus k. So an x minus 2 divisor means that our divisor is just 2. The minus is part of the actual form that we want. Okay. All right, so we've got a line of our coefficients. We've got the k value out in a box. Now we're going to kind of leave a row, and we're going to put kind of an equals line, so to speak, underneath. And now this is how synthetic division works. We start by simply bringing down the first coefficient. So if it's a 1, then we're going to bring 1 underneath the line. And then we are going to take our k value times that 1, and we're going to put it up here underneath our next coefficient. Whoops. Helps if I do the correct one, though. Let me change that. So the 2 times the 1 should give us a 2. That's what we want there under the 0. And then with each column, we are going to add the columns together, which will give us the next number to put under the line. And then the same thing, we take the 2, that was our k, times this next number, and we put it in the next spot under the coefficient. So 2 times 2 is going to give us 4. And then you just keep repeating that process until you've gotten through all the letters. So now we're going to add the column. -5 plus 4 is -1. Taking the 2 times the -1 will give us a -2. 3 plus -2 will give us a +1. And finally, 2 times 1 is going to give us 2. So taking -8 plus 2 will give us -6. Okay, now, what does all of that mean when we finish that process? So we took a 4th degree polynomial and we just divided it by a linear polynomial, 1st degree. Okay, and so that means our result is going to be 1 less degree. So this result in this case is going to be cubic result. Okay, and this is our quotient, the answer we get from division. These numbers will be the coefficients on that cubic polynomial. So we are going to get a 1x cubed. +2 here means plus 2x squared. The -1 next means -x, and then the +1. Now, what about this -6? Well, the -6 is our remainder. And just like if you were dividing numbers, let's say I want to take 47 and divide it by 5. Okay, 5 is going to go into 47 9 times, which gives me 45. And then I get a remainder of 2. And if you remember back in elementary school when you were learning to do this, there were different ways you could deal with the 2. One way was to literally write R2 to mean you had a remainder of 2. One way was to put a decimal point with a 0 and continue, bring the 0 down and continue dividing. And a third way was to actually take your remainder, put it over your divisor, and have a fraction as part of the answer. So if we did that here with this number, we would have 9, and then we would have 2/5 as part of our answer. This is the idea that we're going to use with the synthetic division. We're going to take this remainder of -6, and we're going to put it over this divisor that we were using. So since it's -6, it's going to be a minus, and then the 6 will go over the x minus 2. And this is our quotient. This is the result of taking x to the 4th minus 5x squared plus 3x minus 8 and dividing it by x minus 2. Okay. Now, another piece of information that we need to use and that can be helpful to us is something called the remainder theorem. And the remainder theorem says when a polynomial p of x or f of x or whatever you want to call it is divided by x minus k, so you see that same x minus k form there, the remainder is f of k. So this probably really should be f. So let's make this an f just to not be confusing, okay? So what this is saying is if I use synthetic division, just like we did, and I look at the remainder that I get from dividing by x minus k, that remainder is actually what I would get if I took k and substituted it into the polynomial. And so this can give us a nice little shortcut for figuring out how to evaluate polynomials. You can always substitute in and work it out, but that is going to require some exponents, and depending on the degree of your polynomial, it could be a little bit complicated. Where here, if we use synthetic division, we're really only multiplying and adding. So it makes it a little bit easier. So let's try that. Again, we're going to take our coefficients from our dividend here. So we've got our polynomial in this case. So 2, 6, -3, and 7. And then instead of thinking of it as a divisor, we're really just looking at what this k value is that we're interested in substituting in. And so that is what's going to go out here in the box, our -2. Okay, and then we go through the synthetic division process. So we bring the 2 straight down, the first coefficient, multiply -2 times 2 to get -4. We add 6 and -4 to get 2. So again, -2 times 2 is -4. -3 plus -4 is -7. -2 times -7 will give us a positive 14. And 7 plus 14 gives us 21. So again, this 21 is the remainder from the division. But what this theorem says is that I can also say that f of -2 is equal to that remainder of 21. And if you want to prove it to yourself, you can pause the video for a second, substitute -2 in for the x's in the polynomial, and you will see that you will get the answer of 21. So this remainder theorem just gives us a nice, easy shortcut to doing that kind of evaluation. Another theorem that can be helpful is called the factor theorem. And the factor theorem says that your k value from x minus k is going to be called a zero or root, depending on your class, your teacher, your textbook, of the f of x polynomial function, if and only if x minus k is a factor of f of x. So if you can show that x minus k is a factor of f of x, you call k the root or the zero of the f of x, and vice versa. Now, why is that helpful to us? What does this tell us? Well, think about what you already know about factors. A factor is the result of dividing when you get a remainder of 0. So if we can do synthetic division and we can get a remainder of 0, then that x minus k must have been a factor. Another way to look at this is a 0 or a root is where the graph of the function crosses the x-axis. So if you're looking at a graph and you have a polynomial doing something like this, this has 3 zeros or 3 roots because it's crossing the x-axis 3 times. Well, in each of those places, in order to cross the x-axis, the f of k has to equal 0. Our y values in each one of these are equal to 0. So using the remainder theorem, we're realizing that we need to evaluate f of k using the synthetic division to see if our remainder is going to be 0. So whether you think of this in terms of factors and dividing, or whether you think of this in terms of the remainder theorem we were just using, either way, we're saying that as we start to think about finding these zeros for polynomial functions, it's going to be imperative that we have a way of figuring out values for k that give us a remainder of 0. That's the big picture. That's what we're trying to accomplish as we find these zeros. Okay. Now, where do we start? Do I just start randomly picking numbers and hoping that some of them will give us a remainder of 0? That is going to be long and tedious and take way more time and effort than anyone wants to put into it. So we have one more theorem to help us out called the rational zero theorem. And it says if your polynomial f of x equals, and this is just a fancy way of in general saying what your polynomial might be. It's going to be to a certain degree. You're going to have terms where your degree decreases by 1 all the way down to your constant a of x. Okay, so if your polynomial has integer coefficients, and your a sub n is not equal to 0. So whatever that leading term is actually has some sort of leading coefficient with it. Then every rational 0 of f of x has the form p over q, where p is a factor of the constant, a sub 0, and q is a factor of the leading coefficient, a sub n. And then just as a little side, when the leading coefficient is 1, the possible rational zeros are really just the factors of the constant term. Now, this theorem is a mouthful and it looks a bit complicated, but it's really not. Let's go through an example and see how this works. So we start by looking at factors of p. And p, remember, is going to come from the constant. So our constant in this case is the 6. So the factors of 6 are 1, 2, 3, and 6. However, we also need to include the negative possibilities because it is possible to take a -2 times a -3, for example, and get 6. So we usually write that with plus and minus in front of each of the factors. So it could be a +1 with +6, or it could be -1 with -6. It could be +2 with +3, or it could be -2 with -3. All of those would give us a result of 6. We do the same thing with our Q. And remember, the Q needs to be a factor of the leading coefficient. So in this case, my leading coefficient is this 2 right here. And so I will have ±1 and ±2. So to get the rational, let me actually go back here for a second because I want to make this very clear. Go, sorry about that. To get the possible rational zeros. Now remember, rational numbers are those that can be written in fraction form. Okay, so the possible rational zeros are going to be every combination of p over q that I can get from these two sets of factors. So I can take the 1 over the 1. I can take the 1 over the 2. And again, remember, we've got pluses and minuses, so it's going to be plus or minus each of these combinations. And then I can take the 2 over the 1, or the 2 over the 2. I could take 3 over 1, or 3 over 2, and I could take 6 over 1, or 6 over 2. Okay, now, when we actually simplify these, we'll realize that some of these values are actually repeats. So we don't need to list repeats. We just want one list of possibilities. So we've got a plus or minus 1 over 1, which is 1, plus or minus 1/2, plus or minus 2 over 1, which is 2, plus or minus 2 over 2, which is 1. We already have that, so we don't need to list it again. Plus or minus 3 over 1, which is 3, plus or minus 3/2, plus or minus 6 over 1, which will be 6. And again, plus or minus 6 over 2 gives us 3, which we already have, so we don't need to relist it. So this is the list of possible rational zeros. If there is a rational zero for this polynomial, it has to be one of these 6 values that we've come up with. Technically 12 when you take the positive and the negative. Okay, now it does not mean that every one of these 12 is a 0. So this just gives you a place to start. It gives you a list of values to work with, and then you would start testing these values to see what works, what actually gives you a remainder of 0. But at least it gives you a place to start. Rather than just randomly picking any numbers, you now know it's got to be among these if there's actually a rational 0. Okay, so let's put all of this together. Let's actually find the real zeros. So what I mean by that is we're only looking for real number zeros. We're not looking at anything imaginary for right now. We're going to find the real zeros for f of x equals 2x to the 4th plus 3x cubed minus 17x squared plus 3x plus 6. Now notice that is the same function that we just had in this previous example. So we've already done the first part, which is to come up with this list of possible rational zeros. So we've got 1, 1/2, 2, 3, 3/2, and 6. Let's rewrite this over here so we know what we're working with. Plus or minus 1, plus or minus 1/2, plus or minus 2, plus or minus 3, plus or minus 3/2, and plus or minus 6. Okay. All right, so now we need to start testing these. And so we are going to take a look at different values and use our synthetic division to test them out. So we've got 2, 3, negative 17, 3, and 6 for our coefficients. Now, if you are allowed to, I would highly recommend that you take a look at the graph of this polynomial to get an idea of which of these zeros might be possibilities. If you're not allowed or don't have access to graphing capabilities, then you're just going to have to do some guess and check until you get to something that gives you a 0. Now, I know from looking at the graph that 2 looks like an x-intercept that I could use. So I'm going to test 2. And so when I go to do my synthetic division now, I bring the 2 down. 2 times 2 is 4. 3 plus 4 is 7. 2 times 7 is 14. Negative 17 plus 14 is negative 3. 2 times negative 3 is negative 6. 3 plus negative 6 is negative 3. 2 times negative 3 is negative 6. And 6 plus negative 6 is 0. So this is what I want. That remainder of 0, that's what I'm looking for to tell that, yes, this 2 is one of my zeros for the function. Okay. Now, this result is a cubic. And what we want to do is we want to continue doing synthetic division until we get to a quadratic result. We want the quotient to be quadratic because then we can shift to the quadratic methods for finding zeros, finding solutions. Okay, so I need to do this one more time. I need to choose another value to see if it's going to work or not. And I'm going to use my synthetic division with my resulting quotient. Okay, I'm not going back to the original. I'm going to use the 2, 7, negative 3, negative 3. And so again, having looked at the graph, it looks like I might have a 0 at negative 1/2. So I'm going to test that as my next number using that result. So again, 2 comes down in front. Negative 1/2 times 2 is going to be a negative 1. 7 plus negative 1 will give me 6. Negative 1/2 times 6 will be a negative 3. Negative 3 and negative 3 will give me negative 6. Negative 1/2 times negative 6 will be positive 3. And now we've got another 0. So that tells me that negative 1/2 is also going to be one of the zeros. And I can see now I've gone from a 4th degree to a 3rd degree, now to a 2nd degree, which is quadratic. So now I can take these coefficients and write the quadratic 2x squared plus 6x minus 6 and find the zeros from that. Okay, now finding the zeros is really just what are the x values if I set it equal to 0. So I can do this one of two ways. I can try to factor, or I can use quadratic formula. I do notice that all of my terms have a common factor of 2, so I am going to factor that out first, just to see if that makes things easier. But it doesn't really seem like x squared plus 3x minus 3 is something I can easily factor, so I'm going to use the quadratic formula. Okay, so I'm going to come over here, and I'm just going to use it on this simpler version, because if I can make it a 0 of that quadratic, it's a 0 of the quadratic when it's been multiplied by 2. So I'm going to take the opposite of b, plus or minus the square root of b squared minus 4 times a times c, all over 2 times a. So negative 3 plus or minus. So this is a 4 times 1 times 3, that's 12. The minus and the negative make it a plus. So 12 plus 9 is going to be a 21. 2 times 1 will be 2. And then there really isn't anything else that I can simplify. And so my final answer here for finding the real zeros. Now keep in mind, these zeros that I just found from the quadratic formula, with this square root, this makes them irrational, but they're still real. So they still count as part of my zeros. So I have the 2 from my first trial, the negative 1/2 from my second trial, and then -3 plus or minus the square root of 21 over 2. That counts as 2 different zeros, one if I add and one if I subtract. And so that's my final answer for the zeros of this polynomial. Okay. I hope that you found this helpful. If you would like to see the video for finding all zeros or other concepts that you need to refresh or review, please check out my Gordon Global Math page on YouTube. Videos covering Algebra 2 and pre-calculus concepts will be added throughout the spring of 2025. Thanks for watching.